Well, good morning, good evening, good afternoon, wherever you may be. Once again, my name is Larry Pierce, and thank you for attending today's webinar on the analysis of progressive ply failure in composites using MSC Nastran. Now, I feel sure that most of the people on the call are familiar with composites, work with composites, have heard of composites, have studied composites, used composites in your daily work. You're probably aware that composites use has really exploded in the last, decade or so. You may not be familiar with the fact that glass fiber composites is basically like 86% of composite applications by volume, used a lot in marine, automotive, wind turbines, and other industrial and consumer products. Carbon fiber is also heavily used in industries like aerospace, automotive, offshore oil, wind energy, and sporting goods. We all need to be able to hit our serve a little harder or our golf drive a little bit longer. So composites are used everywhere. And once again, I feel like in talking to this group of people that you're already pretty much aware of that. I also feel that there's some other things that you already know as well and are probably well versed in. And that is some of the advantages of composites. I mean, these are the reasons you use composites in your structural components, whether it be lighter weight, which of course is very important these days, looking for transportation devices that have higher fuel efficiency so they're greener. Lighter weight can be a big contributor to that. But of course, other advantages of composites are high strength to density, high stiffness to density, and lots of other things. And I'm, once again, pretty sure you're well versed in these. But just as you're well versed in the advantages of composites, I'm also pretty sure that you are aware of some of the disadvantages of composites. Composites have more material information than just E and nu that you have with metals. So you have E11, E22, nu12, G12. You have more failure allowables as well. So with composites, extensive testing is probably required. And because of the extensive testing that's required, there's a higher cost associated with that. So in order to leverage all of the advantages to their fullest and to drive down the extra costs from like extra testing, you probably, and one reason you're on this call is you want to simulate more. You want to do more simulation of composites in lots of different areas than maybe you've actually done before. And the reason you want to simulate more, once again, is to leverage the advantages and drive down those additional expenses that you incur. So people are looking to do analysis of composites to reduce the cost of the extensive testing requirements. You're never going to replace the testing requirements, but anything that you can do to replace a test with a simulation is usually a cost saving. The other thing about composites as well is many composites are designed for first-ply failure, and as people drive their structures to the limit and as margins of safety go lower, people really begin to ask the question, well, what lies beyond first-ply failure? Because I've already got a pretty low margin there. So what is beyond first-ply failure? And is this failure an abrupt failure, okay, or do I have some additional load-carrying capability after that that I can count on? People want to know how is the stress redistributed from either ply to ply or just in adjacent elements around in the structure. And people want to know, like, how far is first-ply failure from last-ply failure? And there's other questions. This is just a short list of questions. So as you look to simulate composites more, let me tell you about some of the things that are in Nastran, just a quick overview before we get into the meat and potatoes of today's presentation. MSC Nastran will have been a company for 50 years next year, so we've been a software company for a very long time. And during that time, we've had a very rich history of supporting composite analysis with support for many different element shapes and types, 1D, 2D, 3D, support for many different failure theories, calculating the failure indices, strength ratios, support of optimization in composites, support of progressive failure analysis in composites, and of course today's presentation is going to focus on progressive ply failure. But Nastran also supports the several techniques to study delamination in your composite structures as well. Nastran, of course, provides pre- and post-processing to support all of this capability for Nastran, and even has some additional pre-processing capabilities in something we call laminate modeler, which provides the ability to do a draping analysis and also provides some additional tools for layup management as well. In the rich history of Nastran supporting composites, once again, one-dimensional layered beam elements, layered shell elements. Of course, that's like a workhorse. That's an element that's been around a long time to do composite analysis, as well as layered solid elements. Layered solid elements can either be a more traditional solid element or a layered solid that has additional assumed strain functions to accurately capture bending behavior like a shell element. Of course, Nastran supports the calculation of first-ply failure, either the failure indices or many prefer, and as do I, the strength ratio. Nastran can optimize on the ply thickness or orientation and can use the failure index or strength ratio as a constraint in that optimization. And once again, first-ply failure often is used to sign off a part and say that it's actually a good part or a bad part. As I said, Nastran supports many different failure indices for the calculation of first-ply failure as well as progressive ply failure, including a user-defined criteria if one of the supported criteria does not fit your needs. In the area of optimization, Nastran can do sizing optimization, where we can vary the number of plies as well as the ply orientation, or even the ply material properties for that matter. The objective is typically to minimize weight, but can also be other things such as maximize stiffness. Design constraints can once again be the failure indices, strength ratios, frequency, displacement, stress, any response calculated by Nastran. Another optimization capability in Nastran in the area of composites is topometry optimization, which is the ply-by-ply element thickness optimization. And this effectively gives you an optimized material distribution across all elements. It tells you the optimal ply placement or distribution of the plies. In other words, you need the 45-degree plies here, you need the 90-degree plies here. And a typical topometry optimization problem statement is to minimize the compliance, that is, maximize the stiffness, while maintaining only a percentage of the original mass. So back to So that was just a short overview of some of the optimization capabilities in Nastran. Once again, it's very wide and deep in that area. Now back to kind of the crux of what we wanted to talk about today, which is going beyond first-ply failure. And there's really two big categories here. One is ply material failure. This is progressive ply failure analysis, which is going to be our focal today. But Nastran also supports delamination. Nastran supports three different techniques, I should say, for studying delamination in your structure. First would be virtual crack closure technique, cohesive zone modeling, and also breaking glue. But once again, today's focus is going to be on progressive ply failure. We are going to have another webinar just on delamination later this year sometime. Okay. So to kind of circle back, why are we interested in looking at something beyond first-ply failure? Well, we're trying to drive down the additional cost of composites that often arise from the extensive testing requirements, not only at maybe the material coupon level, but also at subcomponent level, looking at design allowables for joints, etc. So if we can simulate that, we can hopefully save a little money. And once again, many designs these days are actually, the margins of safety are pretty low at first-ply failure. So people are wanting to answer basic questions. What lies beyond first-ply failure? Is it abrupt? How is the load redistributed once the plies begin to fail, etc. So given that we know where first-ply failure is, and that's denoted on my little graph here, we want to see, as the load is increased beyond that, how the load is redistributed from ply to ply and even into adjacent regions of the structure as the load is continually increased. in this particular sequence of images here, we're actually looking at the total damage. So we're actually looking at the elements that have completely failed as we, continue to increase the load. So when you do a progressive ply failure analysis with Nastran, one of the first things you'll do is to select a failure criterion. There are many failure criterion that are supported, as well as user-defined, should one of the ones that are officially supported not quite meet your needs. Some of the theories like Hill, Hoffman, and Sai-Wu, they've been around for a long time. These are kind of workhorses in the industry. These particular failure criteria calculate a single valued failure index. So we don't really know what the failure mode is, but we know we just have a single failure index that is calculated. Failure theories such as Hashine actually calculate multiple failure indices, and the failure indices distinguish between fiber and matrix failure. For instance, Hashine calculates 4 failure modes, fiber tension compression, as well as matrix tension compression. Nastran also supports a couple of variants of the Hashine. One is the Hashine fabric, which is adapted for fabric-type materials, and the other is Hashine tape, which is adapted for tape-type materials. Another theory that's supported by Nastran is the puck theory. This is a pretty popular theory these days. It also distinguishes between fiber and matrix failure as well. And once again, should one of the ones not meet, that are officially supported not meet your needs, and there's hundreds of failure theories out there. You can just do a quick search on the internet and find that out. You can also do your own with the user-defined capability. So when once you've selected your failure criteria and you're actually ready to do your analysis, let's talk about what happens during the analysis. Well, during the analysis, the behavior up to the failure point is linear elastic. Okay, and as we shall see, the solution is actually going to be an incremental solution as well. Okay, so the composite is going to be failed on a layer-by-layer basis. Okay, and upon failure, in other words, when the failure index is greater than 1, the elastic properties for that ply are going to be scaled down. They're going to be degraded, so to speak. Okay. The degradation of the material moduli is selective. That means if the matrix fails, the fiber properties do not change, and or vice versa. Okay, and the degradation can either be immediate or it can be gradual, and we'll talk about what that means in a subsequent slide coming up in just a second. So let's kind of camp out, take a deeper look at this selective property degradation, and exactly what this means to some degree depends upon the failure criteria that you've selected. Okay, if you selected maximum stress or maximum strain, there'll be multiple failure criteria calculated, actually 6 if you're doing a 3-dimensional orthotropic analysis, and each modulus will be reduced separately for each respective failure. That is to say, if the failure is in the 2 direction, then only E22 is going to be degraded. For criteria that have a single failure index, such as Hill, Hoffman, or Sai-Wu, then all the moduli are reduced by the same factor when the failure index is greater than 1. Okay? If you're using Hashine or Puck or one of the Hashine variants, because we're distinguishing between fiber tension, fiber compression, matrix tension, matrix compression, it will truly be a selective degradation where, once again, if we have failure in matrix, only matrix properties will be scaled down. So let's now take a little deeper look at what it means between gradual degradation of the properties and immediate degradation of the properties. Okay? Immediate means that when the failure occurs, that is, when the failure index in the ply is greater than 1, the respective material moduli are immediately reduced to a specified fraction, which the default is 1%. So the moduli are immediately reduced to 1% of their original values. That default 1% is customizable. That's something that you can change if you wish. Gradual means that within an increment, okay, we're only going to decrease the moduli so that the largest failure index is approximately equal to 1. Okay, So we're not going to reduce it all the way to some base or nominal value. We're only going to reduce it enough so that the failure index is, once again, right around 1 again, okay? The stiffness will not be reduced less than some base threshold value, which the default there is 1%. That's the same 1% that we have with immediate. And I did an example just to kind of illustrate this. You can kind of see a load versus displacement graph here where I did the analysis with Gradual, which is the blue line, okay? And I also did the analysis with immediate, which is the red or brownish line in this case. You can see that first-ply failure is basically at the same point, but in the immediate, once we begin to have degradation, it just falls off very quickly, okay? It is, quote, immediate, whereas Gradual, we have, quite a bit more load carrying capability past first-ply failure than we do if we're doing the immediate, okay? So what this kind of means is that the choice between immediate or Gradual really is dictated by the material behavior. You can also notice that immediate really seems to be more conservative in terms of additional load carrying capability, so that would probably be a more conservative approach. But definitely the choice should be dictated by the material behavior, which is something you will know from either published reports or your own testing program that you're having. I should also note that there's additional reduction factors that are available to allow even more control. There's 5 or 6 of these, so that the degradation can be even a little bit more selective than what we've already talked about here. An example of that would be less degradation of the matrix properties in compression than in tension, because many times the matrix can sustain more compression than it can tension. And I think most of us on the call can kind of visualize that. A question that's often asked, because we mentioned earlier all these different element types that are supported for composite analysis. So a common question is, well, what elements are supported for the progressive ply failure analysis, okay? And the progressive ply failure, as well as delamination, I should note, are supported in both shell and solid elements. Shell elements are often used when in-plane behavior is important. Typically, you would probably go to the solid elements when you're more interested in the stress, strain, and the thickness direction. When you're using the solid element, there are multiple layers with integration points in each layers to simulate the ply layup. And we can also do progressive ply failure on the solid elements as well. In addition to the layered solid elements, there's another layered solid element we call a solid shell. This has additional assumed strain functions to allow it to more accurately capture bending like a shell element would. If you're using the more traditional solid elements, you usually have to have several elements through the thickness to capture bending correctly. So let's look at an example, okay, of using progressive ply failure. And I've chosen an example that's actually out of our course materials, the class that we teach on composite analysis using MSC Nastran. It's just an open hole tension specimen. It's roughly 6 inches long, 1.5 inches wide, with a hole in the middle that has a diameter of about 1/4 inch. Okay, I chose to model it with shell elements, and the boundary conditions are that it is built in on the left-hand side, and there's a uniform displacement that's applied on the right-hand side. The layup, there's going to be 15 plies. The total thickness is 0.15. Okay, the fiber orientation, there's a lot of plus or minus 45. There's also a couple of 90s, and there's also a 0-degree ply as well. And as I said, there's 15 plies, and all plies are 0.01 thickness, or 0.01 inches thick. For the material data, I just used the material data that was part of this workshop from our class. The 2D orthotropic properties are shown here, the E11, the E22. For this particular progressive ply failure analysis, we're going to use the puck failure criterion. So this is the data that we're going to use for that. There is the tension limit there's a a material allowable limit for fiber tension, fiber compression, matrix tension, matrix compression, in-plane shear, as well as the puck has some additional property data that's required, and these allowables represent the slopes on the failure envelope. Okay, that's what they represent, and those would be things that you would derive from a testing program. Okay, so let's go now. I will go into Patran. We'll look at a couple of different things. We'll review the model. Okay, we'll look at the loads and boundary conditions, the material properties, the laminate layup, and the solution setup. And recall that I said that for a progressive ply failure analysis, the solution is going to be incremental, so we'll kind of touch on that. And then we'll look at some results. Okay, we'll check out some results. Let me go into Patran here. And I have the model, very simple model. We're going to plot the load and boundary condition markers real quick just to check our loads and boundary conditions. We're built in on the left-hand side, and we've got this uniform displacement of 0.2 of an inch on the right-hand side. Okay. Now let's look at the ply material properties. So I'll just say modify 2D orthotropic, and we'll look at the data that I've entered. So here's the data that I entered for the 2D orthotropic properties, the E11, the E22, Poisson's ratio, etc. I also have entered in data for the puck failure criterion, okay, and I chose to use the gradual degradation method. Okay, so here's all the data that's required for the puck failure criterion, max fiber tension, max fiber compression, as well as these slopes on the failure envelope as well. Okay. I'm actually going to create the laminate layup. I've not actually done that yet in this particular model, so in Patran we'll create a composite laminate. And in Patran I have the ability to create this composite laminate by entering in the data in this spreadsheet here, which is very user-friendly to click on the material, to enter the thickness, to enter the orientation. But I find when I work with customers that oftentimes the layup data is in a spreadsheet. That may not be your particular case, but I do see that quite often because a lot of times you're actually managing a lot of plies. So let's just illustrate how that would work in Patran. We have a button to import or export a CSV file, so I'm going to import a CSV file that has my laminate layup. And if you recall, I said I had 15 plies, so this has 15 plies, and my total thickness was 0.15, roughly 0.15 here. Okay, so I can give a name for my laminate. I call it my laminate, and I'll just hit apply here. So I've created my laminate. All right. Now I can actually assign this laminate to the shell elements. Okay, and we'll just do that real quick. If I can spell, that would be good. This is going to be a laminate, and I'll select my laminate material. And I'll pick this coordinate system for my material orientation because I want the material orientation to be the 0-degree plies to be in the X direction here. Okay? So we'll select an application region now, and we'll select all the elements. And we'll hit apply. It's a great idea when you're doing composites to always verify stuff because there's really more stuff to verify than there is if you're just working with aluminum. So I'm just going to go back and give myself the peace of mind that my material orientation is exactly what I said it was. I want to know what my 0-degree plies are, so let's kind of zoom into an area. And I do see that all my 0-degree plies are going in that global X direction. So that makes me feel good that I've set this up properly, and I'm really ready to do the analysis now. Okay? So speaking of doing the analysis, we've got our elements, we've got our loads and boundary conditions, we've got our material properties. All that's really left is to submit the analysis. We would do that in Patran under analysis. And once again, this analysis is going to be incremental. We're going to apply the load incrementally. We're going to check the failure index at each increment. If it's greater than 1, we're going to start scaling down those properties. If it's not greater than 1, we're just going to keep on going, okay? We're going to keep on going anyway. So our solution type, since it's going to be an incremental solution, in Nastran will be the implicit nonlinear solution sequence that we call solution 400, okay? I will also turn on, it's already turned on, I will turn on the shell shear correction factor, and what this is going to do is the distribution of the shear stress through the thickness is going to be parabolic. So it's going to force it to be parabolic in that case, and I think that's going to be a good thing. Let's also just double check, because I said it was going to be an incremental solution, so we can double check our incremental, our load increment parameters. And I've got this set up. I have a choice between doing like a fixed increment or adaptive or even an arc length. And for this particular analysis, I've chosen adaptive. Okay. Now, I've actually already run this analysis, kind of like if you've ever watched one of those cooking shows, they always show you how to make it, and then it's already been prepared, so we don't have to wait on it to cook. This particular analysis runs actually fairly quickly. But we'll go ahead and just look at the model that I have with results that are already in it. Okay, so it's the same model, and let's look at some of the results data that we get back from this analysis. And some of the things that will be calculated, let me go to like a fringe plot here. Some of the things that will be calculated by Nastran will, of course, be your composite strains in each individual ply, as well as composite stresses in each individual ply. Some interesting data that also gets calculated is the failure mode, okay? In other words, is this a matrix spot failure or a fiber failure? Is this a fiber tension or a fiber compression? So that's also going to be reported. You'll also get the failure index, and you'll also get the strength ratio. You'll notice that you actually get 3 different failure indices and 3 different strength ratios. So you can actually specify more than one failure theory per analysis, but the progressive ply failure only acts on that very first failure theory, okay? In addition to the failure indices and the strength ratios, Nastran will also calculate the total damage for progressive ply failure. This is on a ply-by-ply basis, so this is the total cumulative failure in the fiber and the matrix for that individual ply. You can also get just the matrix damage for that ply, or you can also get just the fiber damage for that ply as well, okay? So let's look real quick. I'm going to make a deformed shape, and I'm actually going to do a deformed animation. I think it looks kind of interesting, so we'll do that. Let's do a true scale, and we don't want the titles and stuff like that. We don't need those. So we'll go back and we'll say animate. And let's say we want 25 frames. So there's actually 25 increments here. So we'll generate an animation very quickly here. We'll let the animation get started. And you can see how the hole, as the failure occurs, you can see how the hole really elongates as the failure propagates all the way through the thickness here. Let's go back. And let's also add to this, let's look and see what the damage is, okay? So we'll look at the total damage through the thickness here. We'll also animate this. And let's not do any averaging between elements, and we'll look at an averaged value there. We'll turn off the title. We don't need the title information. Already set up for an animation, so let's just add on top of our deformed shape animating, let's also add now the total damage. And let's pause the animation, and let's kind of go back to the beginning here. And what we can see is we're looking at the total damage here. So we're looking at, through the entire thickness of this section here, we're basically looking at the total damage, kind of summing up the damage from ply to ply to get a feel for how much of this material through the thickness is still left to sustain any of the load that's being applied. So we can see that the failure is occurring first where we would expect it to occur, at the top and bottom of the hole. Okay, that's where from any classwork you've ever done, you know that the stress concentration, the highest stress is at the top and bottom of the hole in an open hole tension specimen like this. So that's where we're seeing failure first. And we can see how the failure begins to propagate out, how the failure begins to distribute itself Now the load is effectively distributing itself to the adjacent elements as well as adjacent plies. So as we continue to progress through our animation here, we begin to see more and more failure. And once we get red, we're approaching 90% to 100% failure through the thickness of our specimen here. And I like to notice how, as we begin to get more complete failure through the thickness, how the hole begins to elongate here, because we've reduced the material properties down to a fraction of what they really were. So we expect to see more, quote, stretching of the material as a result of that, okay? So I find that very interesting, and I hope you do as well, okay? So let's go back and look at a couple of additional results. In this particular model, first-ply failure is roughly at 0.2 seconds, going from 0 to 1 is where first-ply failure is. It's very close to that point. So let's come in and let's look at roughly where first-ply failure is. So I'm going to look at the failure index. I'm going to do a plot of failure index. And I'm going to look across all the layers to kind of see what the maximum failure index is. Let's turn off that animation. So I can see that my maximum failure index is 0.9. We know a failure index greater than 1 is indicative of failure. Okay, so I know I'm pretty close to failure at this point. We can look at the strength ratio as well. I know many people, and I agree with that, prefer to look at the strength ratio. It gives you more information than the failure index. We know that strength ratios less than 1 are indicative of failure. So we can see we're approaching 1 with our strength ratio, and we can see that we're approaching 1 at the top and the bottom of the hole, and that's where we're expecting failure to begin first, okay? So let's go back and do the failure index once again. I happen to know, because I worked this problem, that ply number 5 and number 11 are 90-degree plies, and we would expect those plies to begin to fail first because the matrix is carrying the load and tension in those particular plies. So let's go and look at ply number 5. We'll look at its failure index real quick, and we can see that it indeed is ply number 5 that has this failure index that's approaching 1, has that strength ratio that's about to be less than 1. And we can see that the location is at where we expect, at the top and at the bottom of the hole, okay? So we really are seeing first-ply failure. This is good. Makes me feel the analysis is correct, because this is exactly where I would expect first-ply failure, at the top of the hole, and I would expect it in that 90-degree ply the first time as well, all right? If I come in here, I can also look at the matrix failure in this particular ply, and I see that I'm beginning to get, so I'm actually already maybe a little bit beyond first-ply failure at this point. I'm beginning to get my little bit of failure at the top and bottom, and it's once again, it's in this ply. If I really wanted to let Nastran tell me where the failure is occurring, in other words, is this really a matrix failure like I think it is, or is this some other failure? Remember that I mentioned earlier that Nastran, one of the things that it tells you is it tells you the failure mode, okay? So let's go back and let's actually plot the failure mode. And we can see that our failure mode at the top and the bottom of the hole is indeed this number 3, which if you look in the documentation, you'll learn that for the puck failure criterion, the first mode is fiber tension, the second one would be fiber compression, and the next one would be matrix compression, or matrix tension rather, I'm sorry. And I may have 1 and 2 backwards here. This may actually be tension. But bottom line is, this is exactly what I expect. I expect matrix tension failure above and below the hole, and that's exactly what I'm seeing in this particular plot. Let's go back and do one other thing that a lot of people like to do when they're doing this particular type of analysis. Let's check and see how, as the load is increased, what is basically the ultimate load that we can carry. So we'll make a graph, because all engineers love graphs. That's a very true statement. So we'll make a graph, and we'll look at the constraint force, and we'll look at the X component of it, and we'll look at that force versus the displacement, okay, the X displacement, and we're going to do this for this node, which is the node that we're pulling on here. So we'll hit apply, and we get a curve, and we can definitely see that there is a plateau here. So there's some point where we sort of reached the ultimate load carrying capability. Any additional load that is applied, in this case a uniform displacement, the load magnitude drops off because we've degraded our properties so much. So let's go back to our presentation, and let's look very quickly at some of the results in a little bit more detail and look at some of the other things that we can kind of draw attention to. Remember, we were looking to determine what happened after first-ply failure. We were looking to see if that failure was abrupt, how the load was redistributed, etc. Well, we know that first-ply failure happened at about 6,200 pounds, and we can see that there is an additional 4,800 pounds that can be carried by the structure before we begin to reach some sort of ultimate load carrying capability, sort of like some kind of post-buckling response structure. We can see that first-ply failure is really not an abrupt failure either. Okay, we see that there is additional load carrying capability past that. When we were looking at the animation in Patran, we were looking at how the load is redistributed over the structure. So this is another piece of information that we can gather from our analysis to see how the load is redistributed over the structure as the load is applied or increased incrementally on our structure in this case. Okay, in this case, I'm looking at how the load is being redistributed by looking at the total damage. So we were able to answer our original questions here. You know, is there additional capacity past first-ply failure? The answer was yes. How is the load redistributed? And we were able to see that. So many of our questions that we had, we're able to get results that we can make decisions on now. One of the beauties of simulating more, okay, is that we really can do more things in simulation than we really have money or time to do if we're doing testing. You can't replace testing, but once you've tested and once you've correlated your analysis to your test, then that gives you a good feeling and lets you step beyond and start asking what-if questions. And some good what-if questions for this particular analysis would be, well, what about different hole diameters? So I did a series of analyses where I looked at the same specimen size but different hole diameters. And you can see that as the hole diameters are decreased, that this ultimate load that we can carry is also decreased. And that's what I would expect. In addition to looking at different hole diameters, I might actually want to look at different laminate layups. So I also looked at that. Originally we had a bunch of plus or minus 45 degree plies. I looked at plus or minus 30 degree plies as well as plus or minus 60 degree plies. As I would expect, the plus or minus 30 degree plies, the fibers are more oriented with the direction of the load. I would expect greater load carrying capability, and I got it. Just as I would expect with the 60 plus or minus 60s, where the matrix is more aligned with the direction of the load, I would expect less load carrying capability. And that's exactly what I got. In addition to different hole diameters or different ply layups, we can look at different loadings. We can even extend to different geometries now because we're beginning to get a good feeling about what we can accomplish. And once again, we've correlated this to test. So in summary, we've looked very briefly at an overview of Nastran's composite capabilities, the different element types. We briefly mentioned optimization. We kind of camped out and took a deeper look at progressive ply failure analysis with Nastran. Nastran can also do delamination with 3 different techniques. And Patran also supplies tools for draping and ply management. And the takeaway is that Nastran does have extensive composite analysis capabilities and a long history of doing composite analysis. We took a deeper dive. We sort of camped out, I like to say, on progressive ply failure. We saw that Nastran supports progressive ply failure for many failure theories with many solution options. Okay, we took a close-up look at an example, which was an open hole tension specimen And we saw that Nastran progressive ply failure can be used in the analysis of composite structures to answer the basic questions such as what lies beyond first ply failure, how is the stress redistributed, what about different layups, different materials, what about different dimensions and different geometries. Okay? I hope you've enjoyed this presentation. I've enjoyed preparing it and giving it.